start off by reminding you of what we did. We said that based on a few principles you can derive the Schrödinger equation as the wave equation for matter waves, because it gives you just the right dispersion relation. And so that would lead Schrödinger to I h bar time derivative of psi equals, and then minus h bar squared over qm Laplacian applied to psi plus the potential multiplied with psi. So that would be the Schrödinger equation. And then you can start to try and solve it for different potentials, for the particle in a box, for the harmonic oscillator, for the hydrogen atom in particular, and you realize that for the hydrogen atom, yes, you get the correct energy levels that you would also have according to Bohr's theory and that fit experiment. Okay, and then the question comes up, what is the meaning of this wave field? Because for other wave fields, we know what is the meaning of the wave field. If we have a sound wave, then we have pressure and density perturbations. Or if we have water waves, then we just look at the height of the water surface. So there's a direct meaning of the wave. Even for electromagnetic waves, in principle, we can measure electric and magnetic fields by having small charge test particles. So in all of these cases, at least it's clear in principle how to measure the wave. Even if it's not always clear what is the microscopic mechanism of this wave propagation. It's clear if you look into elastic waves, yeah, there's the forces between the atoms that make up the crystal, but it's completely unclear for the electromagnetic field, and if you start to ask what is the medium in which electromagnetic waves propagate, then you already run into trouble. Okay, but at least you can measure the electric and the magnetic fields. Now there is no way that we know of how to measure psi itself directly, and in the beginning of quantum mechanics that was therefore very natural to ask what is the meaning of this strange wave field, which by the way is complex, although of course if you insist that all wave fields that have physical meaning should be real valued, you could just take the real and imaginary parts of psi and then write down coupled equations, so that is not the central problem. Okay. Now, we started last time by saying that typically if we have a wave equation like this, which is a linear wave equation, yeah, if you add two solutions, you get another solution. If you multiply the solution by a number, you get another correct solution. So for such linear wave equations, typically we expect that we can build a quadratic construct out of the wave field, which gives rise to a conservation law, which gives rise to energy conservation or momentum conservation and so on. So more generally speaking, there are conserved densities. And often this gives some insight into the meaning of the wave field, you know? Because, for example, for a sound wave propagating in a crystal lattice, you would have the elastic energy stored in the sound wave. And so what is the general concept for such a local conservation law? Well, you find a density ρ, which might be the energy density or the particle density, and you find a current density, which is a vector field, and then you have an equation like this. The time derivative of ρ plus the divergence of this current density is 0, and both of the density and the current density you would be able to express by the wave field at some point and its derivatives. So this would be usually then called the equation of continuity. And the picture to have in mind is really like in hydrodynamics. So for example, in hydrodynamics, the current density is very simply connected to the density and the flow field, because you just have J equals ρ times the velocity field. And then you can try to draw a situation, a typical situation. So you could have this flow field like here. And then obviously what happens is it just transports along the particles, they stream along from left to right, and because they do that, you don't expect the density to change. If the density is constant everywhere, then the density will also remain constant. And that's correct and is compatible with this equation. because if you look at it, the divergence of the current density in this situation would just be 0. Yeah? There is no source and no sink, and so everything is fine. But then if you have a situation where suddenly the current density lines converge to a point, obviously here the divergence would be negative, and so because the divergence is negative, the time derivative of this density has to be positive, and indeed that is what you would observe, because suddenly you have all this extra density accumulating in this point, if there's no mechanism to take out the particles. Okay. So that's the meaning of such an equation. And then the claim is that for our Schrödinger equation, we also get such local conservation law with a conserved density and with a conserved current density. So for the Schrödinger equation, it turns out that such an equation is correct if ρ equals psi squared, or maybe I should explicitly denote the space dependence. So it's clear this density depends on position, and it's just the square of our wave field. And the current density is a little bit more complicated. Now, you will probably have learned this in your quantum mechanics lectures, but chances are you have forgotten how it looks like, and there's a relatively easy way to remember. So you look back at this hydrodynamic situation. There you have density times velocity field. Now the density would be psi squared. What would be the velocity field? It's not entirely straightforward, but remember, we are talking about these meta waves, so for the particles, the velocity, at least classically, would be the momentum divided by the mass. Yeah? And why do I want to express it in terms of the momentum? Simply because we know the momentum operator. Yeah? We know that minus I h bar times the derivative, that is the operator that gives the momentum, and it has to be applied to a wave function. So maybe I should start like this. I take the momentum operator, and in order to make a velocity out of it, I divide by the mass. So then I would have what I would call a velocity operator, and I would apply it to a wave function because that's the purpose of an operator. Now, this would just take the derivative of the wave function and evaluate it at position x. It would still, in general, be a complex number. Also, it doesn't quite fit what we had here, because there we want to multiply the velocity by the density, and the density we already claimed, at least, it is psi squared. So we need to get another psi in there, and the way to do it is just to multiply the psi star from the left. And then it's still not quite correct, but because this would still be a complex quantity, but we can fix it. We can just take the real part. And this then is the correct current density, actually. How would one check this? Well, this is quite easy. You just try to take the time derivative of ρ. Then the time derivative of this psi squared will give you a time derivative of psi in particular. The time derivative of psi, at this stage you just use the Schrödinger equation. And then in particular you get a Laplacian of psi. Now on the other hand, if you take the divergence of J, you know there is already one spatial derivative. The divergence will produce another spatial derivative. So again you get a Laplacian. And so you can at least believe that if you insert this into the Schrödinger equation, you get the correct equation of continuity. Okay. So that is nice. We still don't know what psi means, but at least we have obtained this density. And there's another remark I want to make here. It turns out that both the density and the current density, they do not depend on the Hamiltonian. They do not depend on the precise form of the potential in particular. So that's special. Yeah? It's not like conserved energy density, because that would depend on the shape of the potential. So the meaning of this cannot be energy conservation. That's something we know from this. So what could it be? And then somehow the first guess of Schrödinger was, well, if I look at the hydrogen atom and I plot the wave function, I know that the wave function will have large amplitudes near the nucleus, and then it will decay outwards and will practically go to zero exponentially fast as I go out towards larger distances. So somehow the wave function is concentrated where also classically I would expect my bound electron to be. And the easiest interpretation you could come up with was to say, oh, this is the charge density of a smeared out electron. Yeah? So in my microscopic world, the electron is no longer a point particle, it is smeared out over a certain region. And this is a very confined microscopic region. So the first guess would be that psi squared has something to do with the charge density. Now, at this point we haven't yet said what are the dimensions of the wave function. And we can't tell because the Schrödinger equation is linear, so I could multiply the wave function by any number with any dimension. But it will turn out later that the normalization that we will use is one where psi squared has the dimension of a density, like 1 over volume. So that if I integrate it over volume, I will just get a number. And if I do it like this, then in order to get a charge density, I would presumably multiply with the charge of an electron. So that if I integrate over all of space and the integral over psi squared would be normalized to 1, I would recover the total charge of the electron. This is just the definition, of course. So the first guess would be that this is the charge density of the smeared out electron. And so if we want to draw this for the hydrogen atom, here's my positively charged nucleus, and then when I want to draw a density, it is relatively dense in the near the nucleus, and then it falls off exponentially actually for the ground state. Now, of course you know from your lectures this is not quite the correct interpretation, but it's not so bad actually, because if you look at an atom or even a molecule, often this is actually a very good interpretation for many practical purposes. And for example, when chemists would try to calculate the motion of a molecule as it rotates and vibrates, it's a very good picture that you say, I have my electron orbitals, they're filled with electrons, producing this charge density, and then each nucleus will feel the electric field coming from this charge density. And it will give you exactly the correct results. And the reason it gives you the correct results for this purpose is that the electrons are so much faster than the nucleus. And the reason is simply because the electrons are so much lighter. So as the nucleus moves along very, very slowly, the electron zips around in the molecule and basically covers all the space many, many times. And so from the point of view of the nucleus, it's like a smeared out charge density. I mean, this is even true classically. If you have a very fast moving particle and there's another very slow particle, you will just see a blurred picture. And so for many purposes in chemistry, actually this is a reasonably good picture. And so there's also a technical term here because, you know, the nuclei are slow, the electrons are fast because of the difference in the masses, and the term is Born-Oppenheimer approximation to treat it like this. So there are at least some purposes for which this concept of the Smeardot charge density is quite good. Nevertheless, if you think about it harder, it really doesn't work. And there are many places where you realize that it doesn't work. If you take it really serious, you would say, oh, if I have this Smeardot charge density and everything is negatively charged, then the different parts of this cloud, so to speak, should repel each other. And this cloud should then just explode, which is absolutely not what you see. So this would be the first disadvantage of this picture. Of course, the reason it doesn't happen is that this cloud still represents only one particle, and somehow one particle does not repel itself. But at this point, you can't tell. You could try to fix this. You could say, oh, I have to change my rules of electrodynamics such that all of this density will act on other charges, but it will not be ripped apart. But this would give rise to all kinds of trouble, because then you can't just insert it into the Maxwell's equations as a source density, and so it's really bad. Okay. But then things get even more severe, and the reason is the following. This is still fine as a picture, since these are also microscopic distances, so the typical distance here would be an angstrom, so 10 to the minus 10 meter. And you could easily imagine that even though in more macroscopic settings we really observe particles, if we go down to these very microscopic distances, the electron is smeared out a little bit. This would be still conceivable. But then, of course, what happens if you take this electron and you ionize it out of the atom, and then it flies in free space? And we all probably know from our quantum mechanics lectures, if you just have a wave packet in free space as it propagates, it not only moves along, but it also spreads. And it will spread without limits and become larger and larger. And at some point, you will have a macroscopic wave packet, and then you really get into trouble. And you can make it even worse if you have a situation where you have some scattering. So let me draw this. So assume here you have your little wave packet moving along, and suppose this is relatively constrained so that this is still microscopic and it's not such a big deal. But there would be a scattering center here, maybe an atom or something, some potential. And then after it has scattered from here, of course you will have waves spreading out in all directions. And then they quickly become very large. Yeah? So you don't even have to wait that long in this case in order for it to spread to microscopic distances. And it turns out this was the first situation where the disadvantages of this picture became so important that one could no longer stick to such a simple interpretation. And it was first analyzed by Max Born. the reason he analyzed it was actually to understand this Frank-Hertz experiment. You may know this. After Bohr had his theory of discrete energy levels, the question was how to test this. Of course, you can say, aha, because my photons have discrete frequencies, that's a test, but that's not really a test because Bohr used this as input to derive his theory. And so Frank and Hertz had this nice setup where they just shoot electrons onto atoms, and then the electrons can excite the atoms, provided they have a sufficient amount of energy, and the excitation, of course, will be in discrete steps because the atoms have discrete energy levels. And so the electrons would lose a discrete amount of energy, and that you could observe. So in order to describe these Frank-Hertz scattering experiments, Born really at the time sat down and solved the problem of scattering not just from a static potential, which would be the simpler case that we would treat nowadays in our tutorials, but even for an atom that can itself be excited, so it would be inelastic scattering. The electron can lose some energy. But in the course of this, he then had to realize that you cannot possibly claim that this is a spread out charge of an electron which then spreads out over the distance of a meter or so. This is nonsense, obviously. And so then he proposed, no, what this really means is when I finally detect my electron, because I place a screen out here, I will still detect it here, or here, or here at one definite place. So the measurement will still yield a point-like electron, and the easiest way to understand this would be statistical. So you say this is just a statistical description. Wherever I have a wave, wherever the wave is large, the probability is quite large to detect the electron, and then you don't run into conflict with this point-like electron. So Born came up with this statistical interpretation. Now it's one thing to say, aha, we need a statistical interpretation, and the probability is probably large wherever the wave field is large. It's another thing to say exactly what is the probability density to detect the electron. Now, the way we set this up, it's of course relatively obvious, because if you have a probability density, it should better be conserved, because the total probability to find the electron anywhere should be 1. And so psi itself, or even the magnitude of psi itself, that wouldn't do because it's not conserved. So you definitely need something like psi squared. So you would say psi squared is the probability density. Now just as a reminder, what does that mean? If you ask, what is the probability to detect my electron at one exact point, then as usual the probability would come out to be 0. Because if you specify this coordinate to infinitely many digits, it's just never there. So what you really have to do is to draw a small box around this point, and then you can ask what is the probability to detect my electron within this box. And so if I'm in one dimension for simplicity, this would just mean that psi squared has to be multiplied with the size of this box in order to give me the probability. If I make the box twice as large, obviously the probability will be twice as large. And that's the reason psi squared is not the probability, but the probability density. And so I invite you to go to the website of the lectures and have a look at this paper, because it turns out that most of the paper is of course concerned with all the details of the scattering process, which is quite non-trivial. And then at some point he speculates that psi would be the correct probability density. And then there's a footnote, and it says, on closer inspection, it was realized that psi squared should be the probability density.
So he added it afterwards in the revision of the paper?
Yeah, I guess, I don't know at which stage exactly he added it, but before, shortly before publication, yeah. Probably when he got back the proofs. And this is really the insight that gave him his Nobel Prize in the end. Now, okay, so we know psi squared is at least a good candidate for a probability density because it will automatically fulfill this equation of continuity. Now, even more generally, the Schrödinger equation always conserves probability, at least globally. And the reason is connected to the Hamiltonian being Hermitian. So maybe let me just recall this briefly, why even in general we always will have probability conservation. So the keyword here is unitary time evolution. And you know from your lectures, if I want to get the wave function of the state of my quantum system at some time t, then I can just take the state at time 0 and apply a certain operator to it, which we call time evolution operator. So let me write it like this, u of t. As the time progresses, this evolution operator will change. And it doesn't, so the purpose of this evolution operator is that regardless which initial state I have, I always only need to apply one and the same evolution operator and I will get the final state. And now in particular, if the Hamiltonian is time independent, you know that u of t has a very simple form, it's just the exponential e to the minus I over h bar Hamiltonian times 3. And so you see, for example, if the initial state is an energy eigenstate of the Hamiltonian, then the application of this Hamiltonian to this initial state will just reproduce the eigenenergy. So then this will turn out to be a very simple exponential e to the minus I over h bar times the energy times t. This is the typical time evolution of energy eigenstate. Okay? Now, the important property of this time evolution operator is that it's unitary. So what does that mean? That means if I take the Hermitian conjugate operator, then this is just e to the plus I over h bar, and then the Hermitian conjugate of the Hamiltonian, but of course the Hamiltonian is Hermitian itself, and so this is the same as h. And then you see, oh, this is just what I would have obtained if I take the inverse of my evolution operator. Okay, so that's what it means for the operator to be unitary. And then it's quite simple to show that you have probability conservation. Because what is the total probability in my state? So for example, if I work with a single particle state and position representation, we know that the total probability would just be the integral over this probability density over all of space. Yeah? And so this, however, is nothing but the scalar product of the state with itself. So this is just psi, psi. Yeah, so the probability I always can get by taking the length of the vector, so to speak. And so in our case, then we would check and see psi of t scalar product psi of t is obviously u of t, psi of 0, u of t, psi of 0. And then there's this rule for scalar products that I can pull the operator from the bra part in here by taking its adjunct, its Hermitian conjugate. And then we realize, oh, this is just the identity because it's a unitary operator. And so we find that the norm of this vector is unchanged. And so, at least globally speaking, there is probability conservation whenever we have this Hermitian Hamiltonian. Yeah, because we can always go through this argument. That does not guarantee that you have local probability conservation. Because I could easily write down a Hermitian Hamiltonian that really does the following. It suddenly takes particles from here to there, to the other end of the room, for example. It could still be Hermitian, and the total probability would be conserved. But it's obviously not locally conserved. Yeah? Also, this Hamiltonian, of course, could act on a Hilbert space, which is completely abstract, has a few discrete basis states, and then I don't even know what is the concept of local in space. And in that case, I still have global conservation of probability because of this argument, but I don't know what would be local conservation of probability. So in order to know local conservation of probability, I have to know a bit more about what physical situation we are describing. Okay. So this was just a technical side remark. But in any case, we have this probability conservation. And there's even a nice, there's a geometrical interpretation of this, because a unitary operator is just like a rotation in Hilbert space. So I would start initially from this vector that represents the state at time 0, and then I rotate all of the states in Hilbert space to another direction. But of course, you know, rotations don't change the length of a vector. So, in this abstract geometrical sense, all the time evolution you can have in quantum mechanics is just a rotation in Hilbert space. Okay, so at least now we have something that works for practical purposes, but of course it's just the beginning of our troubles, so to speak. Because in the end, we want to understand, what does it mean to have this probability density? Why does the description have to be statistic, and so on. Now, before we go on at this point, maybe it would be good to understand, in 1926, so when Born had this idea, what kinds of statistical concepts were there around in physics? Because he was not the first to think of something statistical in physics, obviously. Well, so if we think back to the times of Newton and Galileo and Kepler, they had in mind to describe the clockwork universe, the motion of the planets with nice deterministic equations, and the purpose was to precisely predict where will this planet be in 100 years from now. So there was certainly nothing statistical there. And the same goes for all of mechanics and then hydrodynamics. And I guess the first time that statistical concepts were introduced was probably when people realized that if you want to describe the properties of a gas, it would be good to imagine that a gas is actually made up of a lot of small, let's call them atoms, which have the properties of little ping pong balls that bounce around. and which would then exert a pressure on the sides of this container. And if there are sufficiently many, you would not notice macroscopically that it's fluctuating, but still the microscopic picture involves fluctuations, random velocities in all directions. And so this was then made concrete in the middle of the 19th century when Maxwell postulated his velocity distribution as a Gaussian probability distribution for the velocities. And then Boltzmann gave a way of deriving this from some underlying principles, from Newtonian mechanics of the collisions under some assumptions. So in statistical mechanics, we encounter the first fruitful use of statistical ideas. Also, there is the concept of Brownian motion. So if you have a larger particle embedded in this gas of small particles, then it's hit randomly by all the small particles, and then it starts to diffuse around in a random walk. And this was then first analyzed around 1900, and of course the most famous paper is the one by Einstein in 1905. Also, another concept from around this time, or another observation, is radioactive decay, because radioactive decay is somehow the prototypical example of a completely random process, because the probability for one atom to decay per unit time is independent of its prehistory and independent of all the other atoms. So that is a striking example of something statistical. And then, even in quantum mechanics, even at this time, there were already some statistical ideas, because you remember that for photons, people introduced this concept of the energy packets, E equals h bar omega, and then you have to make it somehow compatible with the idea of nice wave mechanics, and at least Einstein's picture was that really you have these many, many wave packets distributed statistically, but overall they would then give rise to a nice plane wave. But if you look at the microscopic level, you would be able to identify all these individual energy wave packets. And so this also goes into the direction of what then would turn into the statistical interpretation. Okay, and then probably the list would be a little bit longer if you look into it more closely. For example, even around this time, people were discussing things such as the shot noise of electrons. So if you have electrons emitted from a hot wire, and then you register all these electrons, you would, well, macroscopically you would just see a current. But then if you detect this more precisely, then you would see that the current fluctuates. And then Schottky came up with this idea that the current is actually made up of many, many electrons, and sometimes during a time interval you would have more electrons arriving, sometimes you would have less electrons arriving, and if the electrons are independent, you can even have a prediction for how large are the fluctuations of the current. So at the time they would not yet be able to register the arrival of individual electrons, but by making this theory, Schottky was able to deduce that if you have this model of the microscopic arrival of the electrons, you get a correct prediction for the size of the fluctuations in the current. And so these ideas were around at this time. Now, some of these ideas have the feature that the evidence is only indirectly. For example, Maxwell-Boltzmann distribution. That's nice to get the correct properties of statistical mechanics and thermodynamics, the gas laws, but they wouldn't yet be able to observe the individual atoms and detect their velocities. Also, for example, Einstein's ideas about photons. At the time, they wouldn't register single photons. They would just register the average intensity, for example. Others, of course, are more direct. For example, Brownian motion, you would already observe the individual trajectory of the particle. Also radioactive decay, you could certainly register the individual events. So we can also ask, what observations were there around this time of individual quantum events or individual discrete random events? And so, well, one example is certainly radioactive decay, because there you could have fluorescence on a screen whenever you have a radioactive decay event, or you can have this Geiger-Müller counter, so that's one thing. Also then, if you think further into the direction of high energy particles, there were then these cloud chambers and bubble chambers with suddenly tracks of individual particles appearing. So all of these would already show individual discrete random events, obviously, but they would not yet really show these in the context of interference, quantum interference. Because in radioactive decay, although now we understand it's related to quantum mechanical tunneling, still once the alpha particle tunnels out of the nucleus, it's gone and the random event has happened, and then afterwards everything is classical, basically. So with regard to quantum phenomena, at the time one only had ensemble measurements. For example, one could measure, of course, interference patterns, then also of electrons, then scattering from surfaces and so on, but you would only measure the average intensity at the time. And this has changed very, very much. So nowadays we can detect single photons, single electrons, single atoms. Basically, we can detect single quanta regardless of which quanta you think of. And so then one interesting point that we have to return to is, how do people actually detect these single quanta? You know, what devices are there for detecting single photons, and what are the shortcomings? How would you detect a single atom, and so on? And of course, because we detect single quanta, we know for sure that Born's interpretation is really the correct one. Okay, are there any questions at this point? Because next is the collapse of the wave function. Okay. So now it's one thing to say that psi represents the probability in the sense that psi squared is the probability density. The next question is probably what happens during a measurement. Because the measurement has this strange feature that, at least according to the standard description, It is an instant in time where you have to kind of interrupt the usual Schrödinger equation evolution, and then you apply another rule, and then you go back to the Schrödinger equation evolution. And so at this point, we don't yet want to discuss, are there ways around this? Can we have a better description? But at least I want to discuss the standard scenario that you would find in textbooks. So suppose we have an electron wave and we somehow manage to detect the position of the electron, and we already agreed that when we detect it, we detect a point-like particle. At least that's the assumption behind the probabilistic interpretation. And the question we want to ask is then, okay, fine, but then after the measurement, what do we do then? We had this Schrödinger equation evolution, which gave us the wave. We suddenly had this detection. And how are we supposed to carry on? Suppose the electron has not been destroyed. Sometimes the measurement destroys the particles, for example, if you absorb a photon. But if it isn't destroyed, how are we supposed to carry on? So how does the wave function evolve after we have detected it at a certain point? And, well, we can just draw a picture. First, say we have the wave function spreading out. Then we switch on our measuring apparatus. Maybe there is a little measuring apparatus everywhere in space, so we give the electron a chance to be detected everywhere. Or maybe there's just a screen here and the electron will hit the screen here or there. But in any case, we detect it at some specific point. Let's say x0. And the question is, what happens then? Now, there are not so many alternatives or not so many options here. We know from now on the electron is here, and if it doesn't make sudden jumps, it will also remain in the vicinity of this point for the first few moments, at least, after the measurement. So if the electron is in the vicinity of this point, probably we should from now on use a wave function that is also localized around this point. I mean, there's not much of a discussion here. And so if the wave function is localized very tightly around this point, of course we also have a feeling of how it will evolve afterwards according to the Schrödinger equation. If we are allowed to apply that again, it will just spread outwards from this point, just as if we had an initial wave function that has been prescribed to be localized at this point. So then we would just have, in the simplest case, spherical waves going out from this point. And so the fact that we first had this extended wave function and then suddenly we have to replace it by a very localized wave function to account for the fact that it has been detected here, that is what people call the collapse. So now this apparently describes what happens in position space, and then von Neumann, the mathematician, came along and somehow formalized it or made it more general. And he would say, look, maybe we just don't want to have only a position measurement, we could also do a momentum measurement or a measurement of any other kind of observable, and at least if we look at position and momentum, they are operators. In quantum mechanics they are operators, and moreover they are Hermitian operators. So their eigenvalues are real valued. And so he would suppose that every Hermitian operator could potentially at least be an observable. And then the question is, if I want to measure one of those Hermitian operators, what should be the prescription? And so here's von Neumann's prescription. And in this case, collapse has been replaced by projection, but it is essentially the same mean. Okay, so the setting, the formal setting is this. We have some operator A, and it's supposed to be a Hermitian, and we call it an observable. And we want to measure it. Von Neumann's theory does not tell us how to do this, but at least it claims to know what happens if you do this. So we have this A, we want to measure it, and then von Neumann, of course, takes his clues from what we know from the measurement of position, and he says, well, you should you should first diagonalize this operator, you find its eigenvalues and you find its eigenvectors, and then the measurement results are the different eigenvalues, which in the case of the position operator would just correspond to all the continuous possible values of the coordinate. Here, for simplicity, I would just imagine I have a discrete spectrum of the operator in order to be able to write it down a little bit easier. And then the rule would be that you obtain as your measurement result one of these eigenvalues, only one of those. And since the whole process is statistic, you want to know the probability for this to happen. And the probability you get, well, here you would get it by taking psi of x squared. Now we just have to have a more formal and fancy way of writing down the same thing. And so what we would do is we would take the state psi, which we want to measure, which is the state just before measurement, and we project it onto the eigenstate phi n of this observable A. And that would give us the probability amplitude to find this eigenstate, and then we would square it, and that would give us the probability to actually find this. And you can convince yourself easily that if you apply the same kind of formalism to the case of the position measurement, you would get the correct result. So this is the eigenstate. And now formally what you have done here by taking the scalar product is you have taken this vector psi, that is the state before measurement, and you have taken its projection onto the direction of this eigenstate. Because you know the scalar product will depend on the angle between these two vectors. For example, if the eigenstate happens to be orthogonal to your state psi, then the probability is simply 0 to find this eigenvalue. But that's not yet quite everything. This just explains what is the probability to find the measurement. This is just like Born's rule, like take psi squared, and this is the probability. We still have to add this new prescription that the wave function has to collapse onto this point, and here it would mean that the wave function has to collapse onto this eigenstate. Because now you know for certain that the system is in this eigenstate, and so in the first few moments after the measurement, if you do the measurement again, you should also find it in this precise eigenstate. So the state has to collapse into phi n. So psi after the measurement is just this eigenstate. And so this is just a more formal way of telling the same story again, in a slightly more general fashion. And it works pretty well for many purposes. Still, it has some disadvantages. And so some of the, well, it depends on your taste, but for me the biggest disadvantage is that it is somehow ad hoc. First you have this beautiful Schrödinger unitary time evolution, and then you're supposed to suddenly switch to such a rule whenever you do a measurement, and only afterwards you're supposed to run the Schrödinger time evolution again. So it sounds a little bit strange somehow. This is not something we are used to from other parts of physics. You know. It's not that in hydrodynamics I have to apply the Navier-Stokes equation and then sometimes for special reasons I just use another rule. Okay, another sort of disadvantage is the following. At least in the early descriptions of this process, one would say, this is my quantum system described by a wave function, and then the measurement apparatus, that's something else. That's a classical system because it also has to go into a definite state, telling me about the position of my particle, so that I should treat differently. And so not only is there this sudden introduction in time of this ad hoc postulate from time to time, but also there's this introduction of a quantum world and a separate classical world. And again, this is a little bit strange, because where should you take the boundary, for example? And so one of the main tasks of trying to develop a quantum theory of measurement is then to somehow get rid of this ad hoc postulate wherever we can and describe the measurement completely within the Schrödinger equation. And of course, as we will see, in order to do that, you also have to describe the measurement apparatus in quantum mechanical terms, and so you have to be able to treat with your Schrödinger equation not just single particles, but really many particle systems. There's another issue here. If you imagine this projection, then the measurement obviously is a kind of instantaneous process. Suddenly you get perfect information of where your particle is. But this is not always true. In modern measurements, which you really analyze in detail, it's often like this, that you slowly acquire more and more information about what state your atom is in, and then you have to apply much more statistical analysis to understand this, because as you slowly acquire this information, also the quantum state, so to speak, slowly collapses onto the final state. So this obviously does not describe so-called weak measurements, which are the kinds that I just described. So this formalism does not immediately cover at least these weak measurements. Okay, and so about all of these points, the modern theory of measurements has something to say. Even though we cannot quite get rid of this Born rule that psi squared somehow means the probability. Okay. Now this is the standard prescription of what you should do formally when you describe a measurement, and it seems to work for practical purposes. But now we want to come back to the statistical interpretation, and we want to ask the question that you should always have as a good physicist, so what happens really? Why is it that there is this statistical description? Yeah? What is behind this statistical description? Okay, so what we really want to understand is what happens at the level of single particles. Because we have this idea, this vague idea that if we have a stream of many, many particles, then psi squared would just be the average intensity of particles impinging on my detector, and that's fine, I just have this vague idea of a stream of many particles. But what happens for a single particle? Because the crux of the matter is the single particle should probably be either here or there if it is supposed to be a point-like particle. And so the example I want to choose again is like this electron wave emanating from the atom after scattering from the atom, like when we discussed Born's description of the Frank-Hertz experiment. Or could also imagine a photon being emitted from an atom and the wave spreads out in all directions. So here's the, say, atom that emits the photon or the electron wave, and then the wave proceeds in all directions. But we know, of course, that if we place detectors out here, at each attempt, when we just emit one electron, only one of the detectors will click. Only one of the detectors will click. So So this is supposed to be the detector, and it clicks. Now, this is quite strange from the point of view of this wave, yeah? Because if the detector were a detector that somehow registers the amplitude of the wave, then this detector here would register the same amplitude as that over there, and as long as they don't communicate, obviously, several of them could click. How does one of them know that the other has already clicked? Yeah? Whereas there's another description which seems absolutely natural to explain this. Namely, if this is just some description of some sort of the probability, then probably what really happens is that initially one particle, and only one particle, is emitted in a random direction, and then afterwards, of course, it will be registered only at one of the detectors, because there's only one particle. So that seems to be a very reasonable interpretation for the fact that you only register one event. So, in one attempt, the particle would go like in this direction. In another attempt, it would go into another direction, and so on. That seems very natural. And actually, if you are only doing this experiment, this is perfectly fine. You won't run into any contradictions. With this explanation, it can easily explain why you observe isotropic probability distribution if you assume that particles are isotropically emitted, and you will only always observe exactly one click. So that seems to be fine. And actually, this is sort of the picture that Einstein had in mind when he first discussed the photons and wanted to discuss, say, the photo effect. That seems to be the picture that he had in mind. Now, how can we, now if this were everything, it would be very nice, would be very natural and not very mysterious. So how can we make this picture fail? And we can make it fail if we do some interference experiment. Yeah? Because here, although I'm drawing this wave, actually the wave properties don't really matter. They would matter if I somehow let the waves reconverge to form an interference pattern, but here it just describes the fact that since these wave fronts are moving outward, they just describe the fact that also particles are streaming outward. Okay. So let's construct an interference setter. And of course, as always, we take the simplest example. And the simplest example for an interference setup, you just need two waves that somehow interfere. And so that would be the double slit. Okay, so let's draw a nice double slit setup. Of course, in order to have interference, just in front of the slits we should have a wave that is really very well extended, so it covers both slits. Then much of the wave will actually be reflected, but we don't care about that part. And smaller parts of the wave will go through the slits, and there they will emanate like spherical waves into the space behind the slits. And so then at some point we will place a screen, and since there is interference between the two waves, we will really see a pattern like this. So that would be a plot of psi squared, the probability density, just at the position of the screen along this axis. Okay, so that's the quantum description. And now we go back to our naive idea. We imagine, well, maybe in reality, as this wave here is emitted from the source, really we just emit particles in a random direction, but it's a fixed direction at each attempt. So then we could have something like this, and we would have a trajectory of the particle. Then at the slit, anything could happen in principle. Maybe there are strange interactions with the walls and so on. So the velocity can certainly change. And then at some other point, the particle would impinge on the screen. And this, at least, would explain the very simple fact that if the stream of particles is very dilute, so that there is only one particle every second or so, then also there will be only one particle registered on the screen every second. And nowadays there are really, there's a very beautiful video of an electron interference experiment where they have reduced the intensity so much that they can see the arrival of individual electrons on the screen. Okay, so this aspect would be covered, but does it cover the interference pattern? Well, the point is, you could always imagine maybe there were very, very interesting, complicated forces acting at the slit, who knows, so maybe I can somehow make it work. Yeah? But we want to go one step back, and we don't want to care about the details of this. We just want to ask ourselves, well, does this naive picture work, that I do have a definite trajectory, even though I don't observe it, of course. Yeah? Now, naively, suppose you have this trajectory, and it's certainly true that, say, the setup is symmetric, half of them will go through the upper slit, half of them will go through the lower slit, but each particle will only go through one of the slits, unless it does funny loops like this. So it only goes through one of the slits. So that should probably mean that the pattern that I observe should be composed of 50% the pattern that I get if particles go through of those particles that go through the upper slit, and 50% of particles going through the lower slit, because there are only these two possibilities. Moreover, I could then try to figure out these individual distributions by, say, closing one of the slits. Now that's where it gets a little bit tricky. You could obviously imagine very long-range interactions of some mysterious nature between the particle following this upper trajectory and the lower slit. Then this could already change something. But if we don't assume that, and physically we don't have any reason to expect these long-range mysterious influences, then I could just close the lower slit, detect the pattern that I observe, close the upper slit, detect the pattern that I observe, and then just add them together, and I will see that I don't get the interference pattern. Yeah? So let's just write this down. So that's our naive idea. So the pattern should probably somehow, classically speaking, be the sum of the patterns made by trajectories only going through the upper and the lower slit. And in addition, if there are no mysterious long-range influences, I could find out these individual patterns by just blocking one of the slits. Now we know this doesn't work because what you observe if you block, say, the lower slit would be a simple pattern like this. More precisely, even then you get some interference pattern, but of a completely different length scale. If you block the upper slit, then you would get a pattern like this, and the sum of those is certainly not the interference pattern. So this contradicts the experiment. Because the experiment really tells you, yes, if I block one of the slits, I get such a simple pattern, but if I open both, I get this nice interference pattern. And so the quantum description of that is relatively simple, because what we actually observe here is a sum of two waves. These are the waves coming from the upper slit and the waves coming from the lower slit. And psi is then the sum of those. At each point, I don't write the argument x, but this would hold at each point. And so if I take psi squared, then this would be psi l of x squared plus psi r of x squared. That is part of the story. But then there's also a cross term where I have to multiply psi l by psi r if I expand the square. And if you analyze it, it's this cross term that makes the interference pattern. Because these terms alone, they would just give this relatively boring smooth pattern, whereas this term here really is responsible for then producing, in the end, the interference pattern. And so this interference term is quite remarkable because, for example, it depends on the relative phase between the waves. If I'm able to change the phase of my electron wave a little bit as it goes through the slit, which I can do, for example, by applying a potential here that gives a phase shift to the electron wave, then this will show up. Then one of the waves, say, so L and R refer to left and right. This, of course, refers to if you look at it from this direction. Otherwise, it would be upper and lower. So, excuse me. Anyway, if you change the phase of one of those, this will not affect the first terms because you just square, you take the modulus square, but it does affect the interference term, and so then the interference pattern would just shift. It would shift up and down if I change the phase in one of the slits. Okay. Now this is already bad enough that I can't just block one of the slits and then observe what happens for those particles with the supposed trajectories going through the upper slit. But it's even worse than that. One does not even need to block the slit. It's already enough to just observe the electron going through the slit. And that is this concept of the Heisenberg microscope, of which you might have heard and which we want to write down now. So the idea will be to try and at least imagine a Gedanken experiment where you observe the electron going through one or the other slit, and observation is really understood in the direct sense of the word. You want to look at it, and you would have to look at it by taking a microscope and shining some light on the electron. The light will then be scattered from the electron. You can also imagine the same experiment with atoms, where probably it would be more realistic. And then you would collect the scattered light by taking a lens, and then you have a picture on your microscope, and you could see, the electron is going through the lower slit, or through the upper slit. Probably you would have to do a very fast photographic process, but anyway, you could determine the slit. And then you could send one electron after the other, and for each of the electrons you would determine, this one went through the upper slit, this one went through the lower slit, and so on. And at the same time, of course, you would also register the arrival points on the screen, and then you would expect what always happens in these experiments, that as you wait longer and longer and more of the electrons arrive on the screen, they would form a nice statistical pattern that would reveal these interference fringes. So that would be the hope. So then you would know both. You would know the trajectories and you would get the interference pattern. But Heisenberg tells us this doesn't work. So again, what is the situation? You have this double slit. You have your electron as it tries to pass through the slit, and then you would shine light onto the electron and would scatter it off the electron. Okay, so now where's the catch? Because the end result of the analysis will be that you destroy your interference pattern. And the catch is here that you want to have a pretty good resolution. You want to be able to tell with certainty that your electron is in this slit or in this slit. And that means, by necessity, you have to take photons that have a very short wavelength, because if you take wavelengths much larger than the separation of the slits, then you won't be able to do it. But if these have very short wavelength, then of course, as you scatter them from the electron, they will impart a very large momentum kick to the electron. And so this momentum kick will be random, and as a consequence, you randomize the position of the electron. And then it turns out, upon closer inspection, that this is not just a feature of your silly idea to use photons, but this is really a completely general feature. Once you try to detect the electron going through one of the slits, that is, you do a position measurement with a sufficient resolution, you will unavoidably perturb the momentum in a sufficient amount as to then destroy the interference pattern. So let's write that down. And so here I'm just summarizing the end result of the analysis. When we then go on to discuss measurement processes in detail, we will see how this really works in practice, and in very concrete examples, how this works out. But here the end result is just if we try to measure the particle position to an accuracy given by some delta x, then we will unavoidably randomize the momentum. And so in a quantum description, you would find this by replacing the original spread out wave function by a wave function that is very well localized. But if you know that a wave function that is very well localized in space is very spread out in momentum space, and so that would tell you that indeed the momentum has been randomized. So if we observe it to accuracy delta x, then we randomize the momentum. And the spread in momentum, the typical spread in momentum, would be given by Heisenberg's uncertainty relation. And so the product of delta p and delta x would be at least h bar half, and so delta p itself should be larger than h bar over 2 times delta x. So whether the precise factors here are reached in any experiment, that depends on the details. You can also do a stupid measurement where the momentum is randomized even more than you would be forced to do by Heisenberg's uncertainty relation. But this is the minimum bound. And so now it turns out that this might be not so bad if delta x is pretty large, because then delta p is not so big. But of course, delta x should not be much larger than it should not be larger than the distance between the slits. It should rather be smaller than the distance between the slits, because you want to have sufficient resolution. And then it turns out in the analysis, if delta x is really smaller than the distance between the slits, then the momentum spread is large enough to completely destroy the interference pattern. So then you draw a lesson from that. If you try to observe the trajectory, it will automatically mean that you destroy your interference pattern. If you want to keep the interference pattern or the more or less unperturbed wave evolution, then you are not allowed to look too closely at your particle. And so that's the lesson they drew from this example. So maybe the general lesson is that observation of quantum particles can strongly perturb their behavior. Now this alone is not completely unexpected if you're thinking of microscopic particles, yeah? Because if you have a big particle, it's relatively easy to imagine that you try to measure it by shining a very weak laser beam onto the particle and doing some interference and thereby measuring the distances. And you can make the beam or your measurement device in general so weak a perturbation that it doesn't really matter. But as you go down to microscopic particles, even a classical physicist would agree that then it's more and more likely that you perturb quite strongly these very lightweight microscopic particles, in particular since your measuring apparatus is also made up of particles of the same size necessarily. You know, if you have atoms, if you have minimum size particles. But what is more striking is that even in principle you cannot make this perturbation small enough by any clever device. But it will always be so large that you are never able to see the trajectory and measure the interference pattern. And that is quite unique, at least classically it would be hard to imagine such a situation. And so this realization is a main part of the Copenhagen framework of quantum mechanics because it teaches you a lesson. You are not allowed to think of trajectories in quantum mechanics, otherwise you run into trouble. And you are not allowed to think of the particle as really having a position and a momentum just before the measurement, but it becomes real only through the measurement, and then via your measurement setup you choose either one or the other observer. So that is the lesson they drew. Okay, so these are the lessons they have drawn. And it's quite remarkable that, although given this example, you agree that apparently it is a bad idea to talk about trajectories in quantum mechanics, there are self-consistent theories that do talk about trajectories in quantum mechanics and are able to reproduce all the predictions of quantum mechanics. So, even though this seems to be a reasonable position to take, given these examples, it's not strictly required, and this will also be a part of the lecture to understand this. Okay, are there questions at this point? Well, okay, if not, then see you on Monday.